Hello, we are Team 5. We will start presentation about Burj Khalifa. We will gonna talk about role of team members, weekly plan, summary, load management, axial and lateral forces, preview of next week. This is the role of team members. Hao Sang-wan and Choi Yan-jun take a role about research and arrangement. Byung Sang-go takes a role about research and writing script. Lee Ji-nung takes a role about PPT planning and making. Zhang Meiji takes a role about PPT designing and making. And Shinotech takes a role about presenter. First, from this week, we will present the problems during construction. First, we prepare for load management. In the last week's presentation, we had presented about the 3-day cycle. The key to the 3-day cycle was to shorten the construction period and obtain the maximum efficiency within a limited budget. Samsung C&T Corporation, which was able to carry out construction to meet these conditions, was adapted as the main contractor and began to construct the Burj Khalifa. This is a review of 3-day cycle. Day 1 has prefabricated a rubber frame on the ground. The assembled frame was installed in the formwork in Day 2. Finally, we pour concrete on Day 3. After this 3 days, one layer is completed, which is repeated as Day 1. To shorten the construction period, in this project, concrete pumping method was used. Also, we solved the problem by securing workability by mixing different materials. In addition to the 3-day process, we will look into the load issues during construction. The load on the building varies. Therefore, load management is an essential element in building design. This affects design and construction, so if the load is not properly managed, then there is a lot of complexity in the next process. In other words, load management requires a deep understanding of materials and structure systems. The load measurement to be considered when constructing high-rise building can be largely divided into axial force and physical force. With axial force, there are dead loads, live loads, snow loads. In other words, it can be seen as a force about gravity. With lateral force, there are wind loads, earthquake loads, impact loads. Especially, high-rise buildings need to be managed for wind loads. A way to manage these loads was needed, so some companies need to find out new managing method. Before constructing Burj Khalifa, buttress core, the latest technology used in Tall Valley 3, was adapted and constructed in Korea. Interested in this method, some companies adapted a method of developing and using buttress core used in Tall Valley for Dubai. Then, what is buttress core? Let's see this picture and understand. Buttress core consists of a core located in the center of a corridor wall that connects the hammerhead wall with the core, and a nose column that connects the vertical members. Also, it has both the ability to resist axial forces as well as lateral forces. Let's move on the next slide and see how they apply to each. From now on, let's see how the buttress core resists the axial force. The buttress core is connected by a corridor wall to the central hexagonal core and nose columns and hammerhead wall. Due to the extreme height of the building, the perimeter column structure was adapted. This is direct outrigger. In this outrigger way, we adapted the load redistribution method of hammerhead wall and nose column. The load flows to the hammerhead wall and nose column along the corridor wall. In this way, even though it is a skyscraper, it can resist the load on the axial force. In this slide, there is rope outrigger. The outrigger used in Burj Khalifa is a composite dovetail-link beam. Not only the axial force on the outer column connected to the outrigger, but also the flexure and shear force may be caused by the rotation of the outer end of the outrigger. If the outrigger are connected, when the load is applied to the outer wall as follows, shear forces are induced in the outrigger to reduce the moment of the core shower. In the previous slide, we presented how to resist axial force. This slide will show you how to resist the lateral force. The representative lateral force is wind loads. The wind load increases the size of the wind load as the height of the building rises. Without the particular resistance method, shaking occurs in the direction of the wind. The technique that some came up with to resist this wind load, exoskeleton and setback tire. Let's find out about each of them. There is an exoskeleton technique designed by some to resist the loads in the Sears Tower, a 442-meter high skyscraper. Let's see schematic description. Structural steel frame is pre-assembled into sections and secured with exoskeleton to resist strong loads. This completed exoskeleton shows a strong resistance from outside the building. Let's see this video. They shifted the steel framework from the inside of the building to the outside. Exoskeleton made it very hard for wind to bend the building. This structure was applied to Burj Khalifa's exterior walls. The Burj Khalifa is comprised of a series of tubes that each have their own exoskeleton. However, Burj Khalifa, which was expected to double the height of the Sears Tower, was difficult to withstand the wind load just with the exoskeleton structure. There has been a series of exoskeleton structures, but the strong winds blowing on skyscrapers create vortex in the leeward, causing the building to shake sideways. As a solution to this problem, some design team and structure team decided to adapt rather than fight against wind loads. Setback tiers refers to a spiral of shape at the top of the building as the height of the building increasing. That's how it was actually applied. By calculating and analyzing the data through the wind tunnel test, the setbacks of three wings were determined to minimize wind power effects. By confusing the wind, this design induces a dishevelled spiral that scatters over the height of the tower. So, you can see the diagram under the wind load as shown in the picture. It allows the wind to pass around it. We certainly wouldn't want the top of the building to sway in the wind. As the building extends upwards, one of the three puddles will shrink in a rotating pattern. So this parallel series and then this one and this one. This gives us a spiral effect away to top. High-rise buildings such as Taipei 101 require mass damper to control wind loads. In the case of Burj Khalifa, the setback tier is shaped in a spiral shape to reduce the shaking caused by the vortex. Therefore, there is no mass damper, which helps space utilization and reduce building loads. Wind loads can also cause torsion by weak flow. Then the outrigger blades again. The three wings place around the core support each other's two wings. When the outer end of the outrigger rotates, core will resist the moment. In other words, by connecting the top and bottom of the outrigger to the outer column, we were able to effectively resist not only the axial force, but also the shear force and the moment. You can check the dynamic frequency analysis that occurs when the wind force is 4.5 meter per sec, 10 meter per second, and 11 meter per sec. These tests and simulations have confirmed that Burj Khalifa is a building safe from the wind loads. It is novel that such a structure system was included in the design, but the building plan of the tower was very difficult in every way. Therefore, monitoring programs for the condition and structure of buildings had to be implemented. So, next week, we will learn about the types of monitoring systems and how they work. This slide is our last slide. Thank you for listening.